So today I'm planning to finish, again, I think I'm not going to prove quite everything I stated in the theorem a while ago, but this will sort of finish the proof. And so in this theorem, this construction of rigidly rotating solutions to older equations was reduced to a certain variational problem. And the variational problem said find some omega that maximizes some energy functional in some space. And the last requirement that we didn't prove is that the support of this maximizer is supposed to be a compact subset of this set S1 where it's confined to live. And so we're doing that now. We proved a bunch of lemmas last time, this so-called concentration lemma, and then some sort of simple facts about this logarithmic energy. So the point is that the energy we're considering is basically so this funny G defined on S naught. Wait, anyway, let's not repeat that. Okay, and then more estimates. And so with that, we had reached this starting point, which was that there exists, so just as an easy, but by combining the previous three lemmas, we found, so remember S1 is this set. There exists a point X in S1. S naught would be a sector here. S1 might look like this. And there exists a point X in S1 who's, and so this goes from a radius 1/2 to radius 2. That was the definition of S1. And X is close to 1, the distance from the origin is close to 1. We can assume it's theta symmetrized. It's on the x-axis if we like. And the vorticity is concentrated around there in the sense that if we look at if we integrate over a ball of radius square root of epsilon, that contains all but order 1 over log 1 over epsilon of the vorticity. And so the complement contains very little. And so then as consequences, we can see that this function psi is the convolution with the extended omega. Okay, so psi is the stream function. Psi is big on this small ball, and if we stay a certain distance away from the small ball outside here, then psi is bounded by, and so here C means a constant independent of epsilon. And so, okay, so this is our starting point. And we also know this characterization of maximizers, that the support of the vorticity is exactly the set where phi is positive. Where phi is what? Phi is this potential plus this quadratic thing involving these Lagrange multipliers, alpha, epsilon, and mu epsilon. And we don't know that much about those guys at the outset. Earlier we proved, yes, right now we don't know much about alpha, epsilon, and mu epsilon. Okay, and so so the goal is using these to prove compact support. Let's do that if we can. So here's the first claim. Let me draw a picture of S1 of the set where everything is taking place. So here might be the circle where R is equal to 1. And I want to look here in some region where the radius is between, I don't know, 5/8 and 7/8. And I know that my small ball is in some place around there. Okay, and so the claim is that if phi epsilon, that phi epsilon is 0 in this blue region. And let's suppose not. So I'll give a proof by contradiction. What do I mean? I mean, I've done something terrible here. Now, this is, okay, this is going to be a huge mess. I'm sorry. I want omega epsilon to be 0 there. And then, in other words, phi epsilon is less than or equal to 0. so the so omega epsilon vanishes where phi epsilon is non-negative, is non-positive. Okay, so suppose not. I think I may run into problems on claim 2 because I thought I had a. Anyway, we'll see what happens. Suppose not, then. Okay, yeah, I'm going to have trouble later on. Sorry. Then so say phi epsilon at some point x is positive. So consider any y where phi epsilon of y is less than or 0. We can find a lot of those points because the set where phi epsilon is positive is exactly the support of omega epsilon. And remember, omega epsilon is it's 1 over pi epsilon squared times the character function of a set, and the integral of omega epsilon is 1. And so the support of omega epsilon is a set of small measure pi epsilon squared. And so it's no problem finding places where phi epsilon is negative. Those are points off the support of omega. And so then clearly phi epsilon of x is bigger than 0, which is bigger than phi epsilon of y. In other words, and the point is this constant mu epsilon appears on both sides. And so, so we can then subtract and find that psi epsilon of x minus psi epsilon of y is bigger than alpha epsilon over 2 x squared minus y squared. Okay, and so here's what I want to do. I'd like to use this to get bounds on alpha epsilon. So my first goal is to show that alpha epsilon can't be too big. And then so okay, and so let's consider 2 cases. So either so alpha epsilon is either positive or negative if it's non-zero. If it's 0, okay, and let's assume positive for concreteness. Then the negative case is similar. So then what do I want to do? So then if I guess x squared is, we know that alpha epsilon okay, there's a factor of 2 someplace. Okay, so we know that, and so what I want to do is just find points. So I have some point here, x, where phi epsilon is positive, and what do I want? I want to find a point y, say down here someplace, where phi epsilon is negative. I can choose y such that y is less than, I don't know what, 5/8, what's, so 9/16. And phi epsilon of y is negative. So again, the set where phi epsilon of y is less than or equal to 0 has huge measure. It has measure all but 1 over pi epsilon squared. 1 over pi epsilon squared. It has measure all but pi epsilon squared. So I can definitely find a point down here where phi epsilon is negative. And then I say to myself, well, then this, for this point, this distance, x squared minus y squared, well, it's I don't know, it's bounded below because x has modulus at least 5/8, y has modulus less than 9/16. And so this is bounded below, and also these are bound. Remember, in this region, psi is bounded by a constant. That was one of our starting points, and so this is just bounded by some constant. Okay, and so then, and so when we, so this is under this, assuming this contradiction argument. Okay, this is bounded by a constant, and then what happens? So now I want to use this inequality again. And so I should say a few days ago, I alluded to ad hoc arguments using the Euler-Lagrange equation. And I said, well, we'll skip those, but here I'm doing them in detail. So I'll use this again. And what I want to do now is to choose a new point, y, over here in this small ball where, and so remember in the small ball rated square root epsilon, I know that psi epsilon is big, and here I know it's small, and so I can achieve a contradiction by right. So I'll choose a y who is well, let's see. Well, let me first remark the case alpha epsilon less than 0 is similar. Then I would just choose a y over here someplace where phi epsilon is negative. Okay, so then so then we've proved this, and what do we do now? We say so now. So now. Choose a y in my small ball. And I can do this because this ball has radius, has measure of order epsilon, whereas the set where phi epsilon is positive has measure of order epsilon squared, pi epsilon squared. So for sure, I can find points in that ball with these conditions. Right? And so let me then look up here again. What do we have? We have a constant minus, and we know that this is like, I don't know, 1 over 4 pi log 1 over epsilon. This is bigger than alpha epsilon over 2 x squared minus y squared. Okay, so this is a negative number because y is bigger than x, but it's not a very big negative number. And on the other hand, this is, and so this is bigger than some constant. Okay, and so this is a contradiction for epsilon small enough. Okay, so in this way we find that there cannot be any point in this blue set where phi epsilon is positive. So we want to show that the support is compact. We'd like it to be localized around here. So far we've shown it's empty in this blue region. The omega is not supported there at all. Okay, one can argue similarly for but you see, I needed points on both sides, both above and below, to reach my conclusion. I seem to have done so. Okay, so okay, so that was claim 1. Claim 2 is that alpha epsilon is bounded by a constant independent of epsilon. And so again, let's remember we have this the support of omega epsilon is the set where phi epsilon is positive. And phi epsilon is psi epsilon plus alpha epsilon over 2x squared plus mu epsilon. And so the idea is to say, well, what is alpha epsilon? Alpha epsilon is I subtract, so I'll write it capital phi minus psi. I differentiate with respect to r and I divide by r. Okay, and so then the idea is to integrate over some part of S1 using the fact that the support using claim 1. Okay, and let me just stare at this for a second. Okay, I'm gonna have to skip that. I had some trick which I realized won't work. So let's omit that. Okay, and then finally claim 3 is, so once we know that alpha epsilon is bounded by a constant, then the conclusion proof is pretty easy. And right, so okay, so then okay, start with that. So then let's finish this. Okay, and so in fact I claim that, well, yeah, here it is. So we have this again, this small ball of radius epsilon to the 1/2, and we know that the support of omega is the set where phi epsilon is positive, and phi epsilon of x is this minus alpha epsilon over 2x or plus mu epsilon. Okay, and so this is psi epsilon of x, and all this other stuff. Well, okay, let's okay, and so here's the point. We know that here in the small ball that we computed that this psi epsilon is bounded below psi epsilon of x was bigger than 1/4 pi, I believe, log 1/epsilon minus some constant in this ball. On the other hand, if we go out here, and if the distance of x to this small ball, well, to the center, say, then we can just compute psi epsilon of x is basically it's this logarithmic integral up to over 1. And so we saw that the the contributions from the other images of the vorticity are bounded. Okay, so we have this, and this is equal to an integral over the ball plus the complement of the ball. Okay, and so in the first integral we know is, so the second integral we know is we've already controlled that. This is bounded by a constant that's from lemmas 2 and 3. We know that the amount of the mass of omega in the complement of the ball is of order 1 over log epsilon, and so this then is of order is bounded by a constant in absolute value. And on the other hand, for here we're looking at this log of x minus x prime, and the distance is, and so this is like, so the point is that the log is like 1/8 log 1 over epsilon if x prime is outside the ball of epsilon to the 1/8, and if x is outside the ball, and x prime is near the center. And so this is like 1 over 2 pi times 1/8 times log 1 over epsilon omega of x prime dx prime, which is, and so the whole thing, I may have been too conservative here. I think 1 epsilon to 1/4 would be enough. This is like 1 over 16 pi log 1 over epsilon, say plus a constant. Okay, and so what do we find? We find that inside here we have we know that the this plasma is big. Outside here is small, and there's no way that and so so again, I'll choose a y inside the ball. Well, actually, for just the center. This is like some constant times log 1 over epsilon, like 1 over 8 pi or something like this, minus a constant. But on the other hand, this is equal to alpha over 2 x squared minus y squared up to a sine. Okay, and we know that alpha is bounded, and we know that x squared minus y squared is bounded because they're all in this bounded region. And so the conclusion is that so I would say, so if right, so what this will tell us is that this this phi epsilon must be negative outside here, because I guess I was going to an argument by contradiction. Assume that phi epsilon outside here is positive, then we would find that this inequality holds, but this inequality can't hold because we would have a constant is greater than or equal to log 1 over epsilon. And so for small epsilons, we get a contradiction. Okay, so that's the conclusion proof modulo, this intermediate step that I skipped. And well, that's all I want to say about this. We spent no time on this. And so I'll try to fill in the correct proof in the written notes eventually. Okay, any questions about anything? Right, let me make some remarks then. So here are a few remarks. Oh, okay, first one. Some of you may have noticed this. So there's a place. So we proved this, we went through this elaborate proof of this theorem. It had several steps, including, conversion to a variation problem, existence of minimizers, compact supported minimizers. So those are the three main issues. And there's a certain place where I cheated. And so you may know this, you may have noticed, or you may have wondered, or also I put this in the notes that were online. But did anyone notice how I cheated in this? I mean, of course, there are many places where I said I'm skipping details. That was cheating, but there's another place where I really sort of skip details without mentioning it. And that was in the following. So when we proved that a solution of the variational problem is gives a solution of the Euler equations, what did we do? So we showed that the solution of the variational problem yields a weak solution of the Euler equations, which involves multiplying by certain test functions and integrating and so on. But in fact, we proved that only for a certain class of test functions. So the lemma variational problem implies Euler in the lemma. The proof had a gap, which I've written this out, or actually I guess I put it in the notes as an exercise, should you want to do it. But here's the gap. So let's see. So the variational problem is posed on this sector, this S0, or there's the set S1 within the sector S0. And so we do everything here, and so we take it, and so what do? We chose the test function phi and we did these perturbations and we got the right identity. But you see, because everything is extended by this, in this periodic way to all of, to the whole plane, if I choose a test function phi with support here and do my arguments, that means that in effect, when I look at the picture on all of R2, I'm choosing I'm proving things only for test function phi with a certain symmetry. Whereas in order to conclude the Euler equations hold, in fact, I need to know this happens for arbitrary test functions phi, not just ones with this rotational symmetry. And so a little argument is needed to go from what we proved to what we actually need. And you can see this in the longer notes posted on my webpage last week, or on Monday, rather. Okay. Oh, another mark. So there, in all of these things, there are trade-offs. And so, for example, when we pose the variational problem, we define this set S1, this smaller set within the sector, and S1 is bounded, its closure is compact, and that makes things easier. That makes it easy to you see, as we'll say in a little more detail soon, weak convergence on an unbounded set is more subtle. More things can go wrong. If you're looking at weak convergence on an unbounded set, then weak convergence on an unbounded set. And so we were forced to rely on weak convergence because we had only uniform LP bounds. So remember, we constructed a minimizer by saying consider a minimizing sequence. We have uniform LP bounds on that. And so that gives us compactness in the weak topology. And so then we can use that to extract limit. On all of R2, or on the whole sector, say, more things can go wrong with weak convergence. And so we kind of got around that by looking at this bounded set. But then that led to other problems, this last step with the compact support within this bounded set. And so there's always this sort of a concentration or difficulty. And the way we dealt with the non-compact domain here was, well, it's one of several possible ways. But that was the trade-off there. Let's see. Oh, okay. So another point is that, in fact, this is I'm talking about a paper from almost 40 years ago, a long time ago, perhaps surprisingly, things like this are still relevant. People are still are still writing papers. Some of them are nice papers, interesting papers with arguments of this sort. And so, in fact, just this morning, a friend of mine recommended to me this. So this is a recent paper. When is it? From November of last year, about sort of a stability. And so this is another, this is instead of a rigidly rotating solution, this is a pair of vortices of opposite signs, plus and minus, who rigidly translate. And so this is a certain stability result. But you can see what it says, that the land dipole is deduced by characterizing a set of minimizers as an orbit by a uniqueness theorem in a variational setting. And so in the end, the variational setting they consider is very much like the one in the theorem we just looked at. So, okay, and then, right. So I would say this approach is in some way, so this is from so people who worked on this in the 70s and 80s were Benjamin, Friedman, Turkington, et cetera, et cetera. And so this is, and so historically what happened is, so these techniques were developed in the context of vortex rings in 3D, traveling stations in 3D, rather than say rotating or translating vortices in 2D, although the problems are pretty similar. The vortex ring problem is more complicated. It's more technical. And so I chose to present this in here, which is a simple thing. In fact, it would have made sense to assume just two vortices. It's easier, and it doesn't. The ideas are the same. But that's what we did. And so these were developed for the vortex ring problem, and so in particular this idea of maximizing an energy subject to within a rearrangement class. So we saw that the problem we posed is a different problem. We didn't constrain our maximizer to belong to a certain rearrangement class. We constrained it to be positive and bounded above and to have, and we constrained a couple of integrals. But the way we proved that it yields a solution to the Euler equation is we proved it was maximal within its rearrangement class. And that's how we deduced a conclusion about Euler. So this approach was pioneered by a guy named Benjamin, Brooke Benjamin, a distinguished English applied mathematician in the mid-70s. And so there's a nice quote. So he in turn was inspired by the work of Arnold, the Russian mathematician Arnold in the 60s. He quotes a paper of Arnold, and I haven't been able to find the paper, so I don't know how similar that. I don't actually know what specific problem Arnold was considering. But Benjamin says something like, well, Arnold's general theory may be hard to implement in practice, but what's important is the underlying idea that there's always an underlying variational principle for these problems. And so, and without putting in a very general framework, one can often just figure out what that is and address by ad hoc arguments. So this is a useful thing to remember. There's always an underlying variational principle. Okay, in the remaining time, I want to briefly discuss, because it's interesting, the approach of Benjamin and Fallrus. So this is gap, which is to say C exercises. And it's a gap just because I didn't mention it at the time. So C exercises in the Fuller online notes. Okay, so so here's let me describe the approach of Benjamin and work that's been done to. And so, in fact, what happened is that Benjamin he stated this variational principle. He said maximize energy within a rearrangement class, and he was a little bit casual about verifying details. And I think he seems not to have appreciated how hard it would be. And so this was eventually made rigorous over a period of, I don't know, 20 or more years, more than that. I think, well, I guess 15, 20 years, by people, notably this guy named Geoffrey Burton in England, and his graduate students worked on this. And so what I'm describing here is the approach of Burton and collaborators to making rigorous the idea of Benjamin. And so, okay, so first is notation. I want to give some definitions. And so earlier I wrote F star to mean the theta symmetrization of omega star to mean the theta symmetrization of omega. Here I will write F star to mean something different. So given a function F on a open set D in Rn, I define F star to be a function of a single variable. And okay, if D is just the positive real numbers, then F star would be the decreasing rearrangement. And so F star is the function of a single variable such that the one-dimensional Lebesgue measure of the set of points where F star is bigger than lambda is equal to, there's a missing equal here, is equal to the n-dimensional measure of the set where the original function F was greater than lambda. Okay, and so this is a different notion of well, it's not exactly a rearrangement, it's a one-dimensional function of a single variable that encodes the information about the size of level sets. Okay, and so then for any non-negative measurable function eta on my n-dimensional set D, I will define, so R of eta is exactly the rearrangements of eta in the sense of before. So it's the set of functions such that when I look at the size of the level sets, that's encoded in this it's a set of functions zeta, such that if I look at the size of the level sets encoded in this zeta star, then that exactly coincides with the same numbers for eta. Okay, so that's rearrangements. But then there are two other sets. There are the this is called the rearrangements of curtailments of eta, and then there's this set W, about whom we'll say a little bit more in a second. And so, okay, so if I have a function, I don't know, that looks like this, then if this is zeta, then zeta star will be a decreasing function. And a so-called curtailment of zeta is one where I take zeta star and I just cut it off at someplace. So it multiplied by the character function of some interval, some finite interval. So this would be an example of, well, okay, sorry, this is a eta. So this is eta star times the character function interval from 0 to beta. Okay, and so then a rearrangement of a curtailment of eta is one whose one-dimensional rearrangement has this structure. Okay, and then finally the last set, and I don't remember what we call W. W is this set of functions zeta such that this inequality holds for all alpha. Okay, and so we can see that if I had equality, then it would just be, again, that's another way of defining of the rearrangement condition. And so this is sort of a relaxation of the rearrangements. It's a bigger set. Okay, so rearrangements would be the set again for which equals holds here. Okay, and so here's what these guys want to do. They would like to approach the variation problem in the following way. So again, my goal is to maximize the energy subject to some constraints. And the constraint I would really like to impose that I'd like to max it in a rearrangement class. I'd like to consider all functions to a rearrangement of some given eta naught. And so I can imagine arguing as follows. I say, well, okay, if eta naught is in an LP space, then all the rearrangements belong to the same LP space. And they're uniformly bounded in that LP space. And so I can extract a sequence who converges weakly in that LP space. And so I want, and so the first, so I take a maximizing sequence, and I can always find a converging subsequence. But the question is, well, what does it converge to? And so the first question is, what are the weak limits or say, what are the limits of weakly convergent subsequences in LP? And it will turn out that is exactly this set W. So W is the weak closure of R of eta in LP. And so then I can say, well, if I maximize a convex function on a, sorry, I maximize a convex function on a convex set, then as a general principle, the maximum must always occur at an extreme point. So it can, so roughly speaking, if I have two, if I can write a point in my convex set as a convex combination of two other points, then because the function I'm maximizing is strictly convex, well, in between these 2 points, it dips down. And so the maximum can't occur in the interior of any segment. It's got to occur at an extreme point. Okay, and so I know that maximizing sequences converge to an element in the closed convex hull. Sorry, in the weak closure, which is going to end up being eta, being this W. And then I have to ask, well, what are the set of extreme points of the weak closure? And that's exactly this set of rearrangements of curtailments of eta. Okay, and so here's this. This is the theorem of Douglas from '94, and so this is really the first. This was needed. This is 20 years after the paper Benjamin. This was needed to really make this approach correct, this kind of thing. And so for concreteness, let me assume that I have a domain of infinite measure. That the finite measure case is easier, and so we avoided these. We avoided issues like this. We avoided some of the possible pathologies of weak convergence by looking at the finite domain. Okay, and so then I assume I have a domain of infinite measure, and I start with some fixed function, a non-negative function on my domain in some LP space for some p between 1 and infinity. Then, okay, so I've already said most of this in words. The set W I defined is, okay, it's convex, it's weakly compact. And this R, the rearrangements of eta naught are weakly dense in W. And so these two points 1 and 4 say both that W is the weak closure of the set of rearrangements, and that W is convex and compact. And so that means I can always find that any maximizing sequence of rearrangements will converge to an element of W, as long as I have some kind of continuity. Well, I guess I'll return to that point in a moment. No, sorry, what is it? Any maximizing sequence will converge to an element of W. And then, and in fact, it will converge to an extreme point. And then, okay, so these are the relationships between the sets. And so, okay, and then in fact, what we want to do is to consider the problem of maximizing the energy, for example, in not only in the set of rearrangements, but we also want to impose constraints such as the integral of intersecting oh no, sorry, that's so the typo is here. So I'm missing T, intersected. Okay, so the theorem is true if I take these rearrangements and the rearrangement of curtailments and this at W, the weak closure, and I interject all of them with the set of functions satisfying some linear constraints, such as the integral of x squared over 2 times eta is equal to 1 or something like that. Okay. And so then what we can do is, okay, so it's also a general fact that a continuous, so I forgot to say this, so a continuous, so to know that so a continuous convex function on a closed set attains its maximum, and that's sort of an extreme point set. Okay, so with these general results, one can argue as follows. First of all, we have to verify. You see, when I say continuous, I mean with respect to the relative topology. The topology is one that will make my set compact, and so that would mean the weak topology. We have to verify that this energy, or E tilde for us, is continuous with respect to the okay, for LP, the weak topology is the same as the weak star topology because LP is a reflexive space, so the stars are redundant. Okay, and so I want to consider things in LP which satisfies some constraints. And in fact, one has to relax the constraints to inequalities, because otherwise you lose convexity of the set. Okay, and so then if I start with A0, that's if it's only an L1, I might have trouble. But if it's in some LP for P close enough to infinity, one can verify that the energy attains its maximum in a set of this form. And then it follows from the previous theorems. So here W is this weak closure of the set of rearrangements. And we know that the extreme points are rearrangements or curtailments. And then one can investigate conditions under which, in fact, the maximum occurs at a point in who is a rearrangement of the original A0. And so this is the program that's carried out by Burton and his collaborators. And so it has two halves. One is the general functional analytic machinery, and the result in the previous slide, which guarantees that these it guarantees sort of the this general part of the argument that the maximum are sustained on a rearrangement of a curtailment, and then the sort of hard analysis part, which is a bit like what we did at the very end. This thing about compact support for maximizers in our setting. This would show that this would be needed to show that the maximum occurs in fact at a point that's a rearrangement of the original function A0. Okay, so this is that program, and these results are kind of interesting. These are really results about weak convergence in LP, and the kind of thing that can happen is you can have I can have a function LP with mass going off to infinity. So that's why one has say inequalities in this definition of W here. That's a typical pathology, or another pathology in weak convergence is that you're going to have rapidly oscillating things converge to something with a different distribution. And so that's another example. But okay, so that's this approach, and you can see once you do this, the advantages are. So we constructed a single example of this rigidly rotating vorticity distribution, and so these are things that look like the characteristic function of a set multiplied by 1 over pi epsilon squared by a big number. And once this is done, one can construct sort of uncountable number of examples. So for every eta in some large class, for every eta naught in a large class, one can in principle construct a solution of the kind we're interested in, this rigidly rotating solution, whose profile looks like this eta naught, or whose vortices are a rearrangement of this eta naught. And so that's interesting. The conditions under which this is true, I mean, so we needed, in our theorem, we needed epsilon to be small enough. In these theorems, you also need you need some sort of corresponding condition which says that the eta naught is sufficiently sharply concentrated. Is that all I have? Yeah, so that's another approach which is kind of attractive. And okay, so what I want to do tomorrow is I'm going to quickly sketch the plan for at least the next month or two, maybe not the whole semester, and then move to the next topic, which is dynamics of point vortices. And I'll fill in the missing part of this proof, that part I skipped today, online in some notes.